Okay, welcome back. The previous example we did was we found the power of a matrix for a general power k, and then applied it for a particular very high value of k, 99. The matrix we looked at was the identity matrix, 1, 0, 0, 1, and we found that the identity matrix raised to any power is just going to result in the identity matrix again. The next example is asking us to do the exact same procedure. Find the general expression that represents this matrix raised to some power k, and then apply it for the power of 99. So we want a to the power of k for all k greater than 1. So we'll find the pattern. So to find the pattern, we have to do an experiment, right? We're doing this experimentally. A squared is equal to a times a, which is 1, 0, 0 minus 1 times 1, 0, 0 minus 1. So we get 1, 0 times 1, 0, we get 1. 1, 0 times 0, negative 1, we get 0. 0, negative 1 times 1, 0, we get 0. And the last entry, we get 0 times 0 plus negative 1 times negative 1, we get positive 1. Okay, that's the identity matrix. Let's keep going. Let's find a to the power of 3. That's a squared times a, or a times a squared, doesn't matter. I'm just going to do it this way. So 1, 0, 0, 1 times a, 1, 0, 0 minus 1. And we'll do our multiplications. First row dot first column. So 1 times 1 plus 0 times 0, we get 1. First row dot second column, 1 times 0 plus 0 times negative 1, we get 0. Now second row dot second column, 0 times 1 plus 1 times 0, we get 0. And now the last one, row 2 dot column 2, 0 times 0 plus 1 times negative 1, we get negative 1. And that's a. Hey, we got the original back. Okay, let's do a to the power 4. A to the power 4 is a cubed times a, which is equal to 1, 0, 0, negative 1 times 1, 0, 0, negative 1. But we already did that. We did that when we did a squared. Take a look. It's the exact same numbers of the same shaped matrix, same shaped matrices. So we're going to get 1, 0, 0, 1. What's a to the power 5? A to the power 4 times a. Okay, so we'll just take our result for a to the power 4, 1, 0, 0, 1 times a, 1, 0, 0 minus 1. I won't label it. Okay, and we get 1, 0, 0 minus 1 after you do the dot products. What's happening? So what is going on here? I'll do one more. That's it. Because you should already see the pattern. But just in case you don't, I'll do a to the 5 times a. So I'll put in a to the 4 I'll put in the a to the 5 that we just found, 1, 0, 0 minus 1 times 1, 0, 0 minus 1, which is the operation we already performed for a to the 4 and a to the power of 2. And each time we got 1, 0, 0, 1. So here's the pattern for those of you that do not see the pattern yet. A to the power of k equals 1, 0, 0, 1 if k is even. So up above I'll put even numbers. Definition of even numbers would be 2, 4, 6, 8, 10, etc. Odd numbers. 1, 3, 5, 7, 9, etc. Keeps going. So we see for all the even powers, a squared, a to the 4, a to the 6, the outcome of a to that power is just going to be 1001. And a to the k is equal to 100 minus 1 if k is odd. So that's the pattern. It's equal to two different things. Just a comment. Actually, it's more than a comment. We can combine these in the following way. This is really neat. Watch this, okay? This is new. This is maybe the first time you've ever seen anything like this in your life. A to the power of k is equal to the following thing. It's equal to 100 negative 1 to the k for all k. Let's think about why. Let's think about why this expression captures both cases up above. Let's do a test. What happens if k is equal to 1? Oh, I should say all k greater than 1. It's greater than equal to 1, but the question is asking for k greater than 1. Well, let's do k is equal to 1 anyway. If k equals 1, we have negative 1 to the power of 1, which is just negative 1. We get our original matrix back. What if k is equal to 2? Then we have negative 1 to the power of 2. What is negative 1 to the power of 2? Negative 1 squared is equal to negative 1 times negative 1, which is positive 1. The negatives cancel. What is the next one? A to the power of 3. That's 3 negatives. Negative 1 has negative 1 has negative 1 multiplied together, which is going to be negative 1. And that recovers our a to the power of 3 expression. And this is the best solution. That is the answer. So put it thus. A to the power of k is equal to that thing for all k. Now we'll apply it. A to the power of 99. So, solution is, notice that 99 is odd. It's an odd number. It's not divisible by 2. Even numbers are evenly divisible by 2. Odd numbers are oddly divisible by 2. Great fractions. So, a to the power of 99 is equal to 100 minus 1. Or you can just use the formula, negative 1 to the power of 99 for the bottom right entry, which means negative 1 multiplied by itself 99 times, so an odd number of negative signs, which is going to end up with a negative. All right, another example. The exact same, is that the last one? Yes, thankfully, it's the last one. But when you look at the practice tests, you'll see a whole bunch of variations of this. So in this example, we're asked to do the same thing. We want to find what is a to the power of k for a general k, and then particular case, what happens if k is equal to 99. On the practice test, you'll see a to the power of whatever year it was on that practice test, although that's not a tradition you can count on. A to the power of 2016, a to the power of 2017. Anyway, so we'll find the pattern, because what we want, a to the k for k greater than 1, and want a power 99. So we'll find a squared, we'll find a cubed, we'll find maybe a to the 4, we'll find as many as we need. So like again, no one's in front of me. No one can put up their hand. Because the most common question, the question everyone should be asking is, how many of these do we have to do? Like, here I stopped at a to the power of 6, but what if I saw the pattern as soon as I got a to the power of 3? Fine. As long as you're confident, as long as you think it's right, that's enough. That's the real answer. When are you satisfied that you've seen the pattern? So for this example, you may not be satisfied that you've seen the pattern until you do 4 of them. Someone else may say, you know what, I'm still not happy, I'm going to do 5. That's just the way it goes. There is no right answer because we're not actually proving it. We're looking at a pattern and we're saying that I'm pretty sure this is consistent and it's going to keep happening this way and that the answer is going to be this thing at the very end. Proving it's a different matter. We will not worry about that. Let's find a squared. A squared is a times a, and that's going to be 1, 1, 1, 1 times 1, 1, 1, 1. Gotta be careful. We got 1 times 1 plus 1 times 1, that's 2. And then each of the other entries is the same, 1, 1, dot, 1, 1. So they're all going to be 2. We won't have to do it once. Okay, now we're going to do a to the power of 3. Now, and don't stop here, because someone's, here's the danger of stopping too early. Like, 1, 1, 1, 1, 1, 1, 1, and then 2, 2, 2, 2. I bet it's 3, 3, 3, 3. It's got to be 3, 3, 3, 3. So the answer at the end is 99, 99, 99. No, it's not. I'll show you why. Let's actually do a to the power of 3, which is a squared times a. Don't celebrate too early when you're doing these, because a pattern might be more complicated than you think. 1, 1, 1, 1. So let's do the dot products. First row, dot, first column. 2 times 1 plus 2 times 1. It's not 3, it's 4. And they're all 4. They're all going to be the same. They're all 2, 2, dot, 1, 1. So 4, 4, 4, 4. Okay, and again, you got people thinking too smart. Not thinking dumb enough. Thinking dumb, thinking smart, these are relative terms. Don't guess is what I kind of want to say. Just don't guess. Be confident. The next one, is it 6, 6, 6, 6? Is that what's going to happen? Or is it going to be something else? Is it going to be 8s? So let's see. Let's actually do one more, at least one more. A to the power of 4 is a to the 3 times a. So 4, 4, 4, 4 times a, 1, 1, 1, 1. So 4 times 1 plus 4 times 1, it is 8. And they're all going to be that. They're all going to be 4, 4, dot, 1, 1. I'm going to do one more. No, I'm not. I'm just kidding. Just kidding. I'm not going to do one more. And now I'm going to look for the pattern. The 2, 2, 2, 2s. Those are all 2 to the power of 1. 2 to the power of 1, 2 power 1, 2 power 1. No, not 2, what do I do? 2 power 1. Hey. It's going to have half between a 1 and a 2. The next one is 2 to the 2, 2 to the 2, 2 to the 2, 2 to the 2. Hey, I did it again. What's going on with me? 2 squared is 4. How about 8? Can you write 8 as 2 to a power? And yeah, you can write it as 2 to the power of 3. 2 times 2 times 2. 2 to the 3 times 2 to the 3 times 2 to the 3 times 2 to the 3. Now what? What do you think a to the power of 5 would be? It's going to be 16, 16, 16, 16 from the pattern. What is that going to be in terms of 2 to a power? 2 to the 4, 2 to the 4, 2 to the 4, 2 to the 4. What's a to the 6 going to be? A to the 6 is going to be, do I have another slide? There's more space. Oh, no, I need more space. It's okay. We'll manage. It's going to be 2 to the 5, 2 to the 5, 2 to the 5, 2 to the 5. So notice that a to a power, a to the power of 6, every entry is going to be 2 to one lower power than that. So, pattern. Aha, I think I figured it out. Pattern, what is a to the k? So I want to write, like I want a blackboard. I want a board I can write on and then like quickly erase it if it's wrong. I want to propose something for you. I want to make a proposal for the answer and then have you tell me why it's wrong. But I can't, so I'll have to tell myself why it's wrong. It's going to be, is this true? I'll put a question mark here. Question mark. 2 to the k, 2 to the k, 2 to the k, 2 to the k. Question mark? Is this the answer? No, it's not, because it doesn't match all the ones that are above. No. Because look up here. A to the power of 2, the entries are not 2 to the 2, they're 2 to the 1. A to the 3, the entries are not 2 to the 3, they're 2 to the 2. These ones, a to the 4, they're all 2 to the power of 3. It's always reduced by 1. So I'm going to fix it. I'm not going to leave that error there. It's actually 2 to the power of k minus 1. 2 to the power of k minus 1. 2 to the power of k minus 1. It's all one lower power. So that was not easy to do. That was a non-trivial type of pattern to find. Now let's apply it. Let's find a to the 99 is equal to 2 to the power of 98, 2 to the power of 98, 2 to the power of 98, 2 to the power of 98. And that would be the answer. We would leave it that way because what is 2 to the power of 98? Some gigantic number, and I don't think you have enough room on a page to write that number. Okay. In all the operations that we've been doing, we have not made use of any kind of interesting or exciting matrix properties. And there's a whole bunch of them. There's a whole bunch of opportunities to take shortcuts when you're doing matrix operations. And they're listed here. I'm not going to read through, well, I will read through all of them and make comments about them. The first property is that order of addition, like numbers, order of addition does not matter. A plus B is the same as B plus A. Now we lose that for multiplication, but not addition or subtract. Or okay, subtractions, I mean, order matters always, but for addition, it does not matter for these. Another addition-related property is that if we have three things that we're adding together, we can add those in any order as well. We could add the last two items and then add the first one, or we could add the first two and then add the last one, or we can add the first and the last and then add the middle one. It's all going to result in the same outcome. The next thing here is that if we add a matrix to the correct size zero matrix, so zero matrix of the correct size of A, we'll get the original matrix A back. So adding nothing, adding the zero matrix to the matrix of the same size, will give you that same matrix back. If we add a matrix to the negative of itself, we will get the zero matrix of whatever the size of A is. Of size A. Okay, and then if we have three matrices multiplied together, A times B times C, we have to keep them in order, but within that order, we can multiply them either doing A times B first and then multiplying by C, or we can do B times C and then A times that, and both will result in the same final answer. The next property is one of the most important properties, so I put a star beside it. This is extremely important. It says that a matrix A times the identity matrix of appropriate size. So I can't say, I mean, you can, it's just the number of columns of the identity matrix has to be equal to the number of rows of A for the first one, and the other one's the other order. So A times the identity matrix is A, and identity matrix times A is A, as long as the sizes match up. This is like multiplication by 1. If you take a number and multiply it by 1, it doesn't change the number. If you take a matrix and multiply it by the identity matrix, it doesn't change that matrix. So this is like the identity matrix behaves as if it is like the equivalent of the number 1 for matrices. Identity matrix behaves like the number 1. Since 1 times 5 is 5, 5 times 1 is 5, and so on. The next property is that you can distribute addition. If you have A multiplied by B plus C, you can distribute over that. You can write that as A times B plus A times C. Now, more likely is to go backwards. If you have A times B plus A times C, it's better to factor out the A. So A bracket B plus C, do that matrix addition, and then do a single matrix multiplication instead of two matrix multiplications followed by an addition. So just to save some operations, for efficiency. And that also works in the other order. B plus C times A is equal to B to A plus CA. So you can common factor on the right and you can common factor on the left. So normally used like a common factoring. And the last one is for scalars, that if you have a constant, a scalar A, I keep calling them constants, a scalar little a multiplied by matrices B plus C, you can distribute that A times B plus A times C. But again, the common way we're going to use this is backwards. If we have, let's say, 5 times a matrix plus 5 times another matrix, we can just write it as matrix plus matrix, all multiplied by 5. We would do that because adding larger numbers together is harder than adding smaller numbers together, and multiplying by 5 would make the numbers larger. No, maybe it'd be better to not use that property if that little a was, let's say, 1/2, 1 over 2, and then all the elements of B and all the elements of C were even numbers. Then it would be easier to do the multiplications first and then the additions, but that's not likely to happen. So we typically do this as a factoring property. And we can also factor if it's two numbers added together. So if we have little a times the matrix big A and plus little b times the matrix, the same matrix big A, we can common factor the A plus B out. Multiplications by scalars, we can do the same thing. If we have, let's say, a number times a matrix times a number, we can common factor out that big number and multiply the two. We can common factor out the little b, multiply it by the little a first, and then do a single scalar multiplication instead of a sequence of two scalar multiplications. The other properties shown here are fairly obvious. If we multiply a matrix by a scalar value 1, we're just going to get the original matrix back. If we multiply a matrix by a scalar value 0, we're going to get a 0 matrix back. And if we do a matrix multiplied by the 0 vector of appropriate size, we'll get an appropriate size 0 vector as a result. 13 is related. If we take any constant and multiply it by a 0 vector, we get, or a 0 matrix, we get the same size 0 matrix. And the last three properties here are the different ones. They say something maybe new, that, well, 14 doesn't really. It says that you can common factor a constant out of a matrix and then perform a matrix multiplication and then multiply by that constant. So we'll do that sometimes. Property 15 is interesting. It says that A plus B all transpose is equal to A transpose plus B transpose, whereas A multiplied by B all transpose is not equal to A transpose B transpose is equal to B transpose A transpose. And I explained that last one. I think the last one is the most, or the least trivial. It's the most complicated one. I explained that in a previous slide, in a previous video. Okay, and then we'll pick up on this in the next video.